Hi everyone, welcome to Unprocessed Math. In today's lecture, I'm going to talk about Fundamental Theorem of Calculus. So suppose the graph of function f is given, that's the pink curve here, and we want to find the area under the graph of f between 2 points A and B. That's going to be this area shaded in green. So the Fundamental Theorem of Calculus provides a very easy and straightforward way for computing these areas. And you can actually view Fundamental Theorem of Calculus as a grand area formula. So the Fundamental Theorem of Calculus tells us that if you want to find this area here for any function f, if you can find an antiderivative for this function f, okay, let's call it capital F. So capital F is an antiderivative for little f. You see that by definition, it means that the derivative of capital F is little f. So if you can find an antiderivative, then in order to find the area under the graph of a function f, all you need to do is just to subtract the value of the antiderivative at the endpoints. So you see this function capital F is an antiderivative for f, and this whole definite integral is actually equal to the value of the antiderivative at b minus the value of the antiderivative at d. And you see that this provides a very easy way for computing areas. So let's see an example. So given this function y equals x squared, you can like to find the area under the graph of that function between 0 and 1. So lambda, an antiderivative for x squared is x cubed divided by 3. So 2 plus 1 is 3. So that's the antiderivative becomes x cubed divided by 3. And so using Fundamental Theorem of Calculus, the area under the graph of that function that is 0 and 1, denoted by this definite integral, is going to be equal to the value of the antiderivative at 1 minus the value of the antiderivative at 0. So if you substitute x by 1, you get 1 cubed divided by 3, and you substitute x by 0 here and subtract. If you compute this number, that's 1/3. And so this using Fundamental Theorem of Calculus, you see how easy it becomes to compute the area under the graph of this function. If you watch the previous lecture, you see that in the previous lecture, we used Wiener sums to compute that area, and the complications are very involved. But using Fundamental Theorem of Calculus in one line, you can compute the area. There's another way to write down these computations. So if the standard notation sometimes is that if you want to compute this definite integral, then you find the antiderivative for x squared, which is x cubed divided by 3. And then you draw this straight line, and you write the lower bound here and the upper bound there. And this notation means that substitute x by the upper bound by 1 and substitute x by the lower bound by 0 as subtract. So you see, I substitute in this expression, I substitute x by 1. That's what I get. I substitute x by 0. That's what I get. And subtract. So it's basically doing the same computation in a slightly different way. So let's look at another example. In this example, we might find the area under the graph of sine and between 2 points 0 and pi. All we need to do is to find an antiderivative for sine. And the antiderivative of sine is one antiderivative is minus cosine. You see that if you differentiate minus cosine, you will get psi. And this needs to be evaluated between the upper bound and the lower bound. If you substitute x by upper bound, you will get minus cosine of pi. So in this expression, I'm substituting x by the upper bound, which is pi. And you substitute again x by the lower bound, which is 0. And this is what you get. And you subtract, right? So what I see here is the expression. Then I substitute x by pi, and this is the same expression. Then I substitute x by 0, and I subtract. Cosine of pi is minus 1. Cosine of 0 is 1. And you have the same minus sign here. So, and if you simplify these numbers, so this becomes plus 1, minus signs cancel, you get a plus 1. Same here, minus signs cancel, you get a plus 1. So 1 plus 1 becomes equal to 2. So the area under the graph of sine between 0 and pi is equal to 2. I want to find the area under the graph of the exponential function between minus 1 and 2. That's the area shaded in green here. Again, you just simply apply the fundamental theorem of calculus. So the area is going to be equal to this definite integral, and all I need to do is to find a non-derivative for e to the x and evaluate it at these 2 points and subtract. So the antiderivative for e to the x is e to the x. It needs to be evaluated between the upper bound and lower bound. That means that substitute x by the upper bound by 2. That will give you e squared. And substitute x by the lower bound, which is minus 1. And you will get e to the minus 1 as subtract. So the area of this green shaded region is equal to this one. So here I want to evaluate this definite integral of this function between 0 and 1. And by definition, it's going to be the area under the graph of this function between 0 and 1, but we don't need to graph it, we just want to compute it. So again, we need to find the antiderivative for this function. Antiderivative of x cubed is x to the power 3 plus 1, which is 4 divided by 4. This is the antiderivative of x cubed. And then I have the minus sign, I keep the minus sign, and antiderivative of cosine is sine. And antiderivative of 2 is 2x. And that needs to be evaluated between the lower bound and upper bound. That's how we write it. So this notation now means that substitute x by 1, substitute x by 0 in this expression, then subtract. If I substitute x by 1, this is what I'm going to get. I will get 1 over 4 minus sine of 1 plus 2 times 1. And if I substitute x by 0 here, this is what I'm going to get. But you know that sine of 0 is 0, 2 times 0 is 0, 0 divided by 4 is 0. So this is going to go away. That's 0. And this is all you have. So that's going to do 1 over 4 minus sine 1 and then plus 2. This is a number you can put it in your calculator. And which is not the point here. So so this is this definite integral equal to this number, which is the area under the graph of this kind of complex function. So you see how fundamental theorem of calculus helps us to evaluate the areas under the graphs of these functions in literally in 1 or 2 lines. So there's another form of the fundamental theorem of calculus, which tells you that if you so you had this function that depends on x. So if you integrate from a to x of any function, ft dt, if you differentiate it, the fundamental theorem of calculus tells you that it's going to be equal to fx. So you see, and this is again, this goes back to the lecture where I talked about antiderivatives. And so you see that, and there I mentioned that integration and differentiations work against each other. So this form of the fundamental theorem of calculus tells you that when you're differentiating an integral of this form, so the differentiation cancels the integral sign, and what comes out is just a function f evaluated at this point x. So every time that you have a problem like this, all you need to do is just to substitute t by x, or whatever variable that you have there. So let me show you an example. So suppose I want to differentiate, so this function is a function of x that depends on x. Suppose I want to differentiate that function with respect to x. All I need to do is just to substitute t by x by the upper bound here. And that's going to be the derivative. So the derivative of this kind of complicated looking function can actually be written directly. So that's going to be equal to arctan of sine x, which you get by just simply substituting t by x there. And this is another example. Suppose I want to differentiate this function. Again, so you see it doesn't matter what lower bound you have. So if you want to get the derivative of this function, all you need to do in this function, substitute t by x. So you get e to the cosine of x. So you see, every time that you want to differentiate functions which are in the form of an integral, so the differentiation becomes very simple. So the derivative is simply the function inside evaluated at x. So you don't need to do any computations. You just take this function which is inside and you substitute t's by x, and you already have the derivative. So for additional practice, you can look at the Apex Calculus 2 textbook. So this is section 5.4. And for any additional help you may need, visit mathematicians.com.